The blast furnace at Riverside Iron Works stands 78 feet tall, its brick shell wrapped in bands of iron that circle the structure like the hoops on a barrel. Inside, the temperature climbs past 2,500 degrees. Limestone, coke, and ore descend through layers of fire, while molten iron pools at the base, tapped twice daily into channels that glow white in the foundry darkness. The night shift foreman, William Mercer, walks the perimeter with a measurement rod, a ritual performed every 6 hours since the furnace first came online in March of 1891. He positions the brass-tipped rod against reference marks cast into the foundation blocks, then raises it vertically along the brickwork until it reaches marks scribed on the iron bands. The distance should match the engineering drawings exactly, 12 feet, 7¾ inches from foundation to the first hoop. The rod comes up short by ½ an inch. Mercer checks his instrument, repositions, measures again. Still short. He moves to the opposite side of the furnace, where the heat radiating from the shell makes his eyes water. Same result. He records the discrepancy in the logbook without comment, circles the entry twice, and continues his rounds. The furnace has been in continuous operation for 8 months. It has produced 4,000 tons of quality iron. And now, while burning at full capacity, while everything inside runs exactly as designed, the external dimensions are wrong. The brickwork hasn't collapsed. The iron bands show no visible damage. The foundation remains level and true. Yet somewhere in the physics of fire and compression and the behavior of materials under sustained heat, the structure has begun to contract. Not catastrophically, not all at once, but measurably, methodically, as though the furnace was slowly pulling itself inward while consuming ton after ton of ore. By morning, 3 separate measurements confirm what Mercer recorded in the night log. The blast furnace at Riverside Iron Works is shorter than it was 6 months ago, and it's still burning. The first meeting takes place in the engineering office on November 14, 1891. Site Superintendent James Holbrook spreads the original construction drawings across a pine table worn smooth by years of blueprints and measurement disputes. The drawings show every dimension of the furnace, the taper of the stack, the thickness of the refractory lining, the precise placement of each iron band. Numbers verified during construction, checked against standards, approved by the consulting engineer who designed the installation. Foreman Mercer lays his logbook beside the drawings, 6 months of measurements, recorded in careful columns. The pattern emerges immediately, a steady decrease in vertical dimensions, roughly 1/8 of an inch per month, accelerating slightly in recent weeks. The change appears uniform around the circumference, but varies with height. The lower sections show more contraction than the upper reaches of the stack. Could be settlement, offers Thomas Kirby, the head mason who supervised the original brickwork. Foundation moving under load. But the foundation shows no cracks, no differential settling, no evidence of subsidence. The leveling instruments mounted at the corners remain true. Whatever is happening, it's happening above ground level in the furnace itself. They measure again that afternoon, this time with surveying equipment borrowed from the railroad yard. Transit level, plumb line, steel tape pulled taut and read to the nearest 32nd of an inch. The results match Mercer's brass rod readings. The furnace has contracted 13/16 of an inch in vertical height since May. The iron bands, which were installed with deliberate clearance to allow for thermal expansion, now sit tight against the brickwork with no visible gap. One of the younger engineers, a man named Simmons Fresh from Technical College, suggests they shut down and inspect the interior. Holbrook dismisses the idea immediately. The furnace is under contract to deliver 30 tons daily to the railroad construction project upstate. Shutting down means weeks of cooling, weeks of lost production, and the very real risk that rapid cooling will crack the refractory lining beyond repair. We measure, we document, we watch, Holbrook says. We don't stop iron production on a theory. So they measure. Every shift, every day, building a record of something that shouldn't be possible. A structure contracting while exposed to heat that should, by every principle of thermal expansion, be making it grow larger. By December, The contraction has become visible to anyone who knows where to look. The access platforms bolted to the furnace at fixed heights no longer align with their corresponding penetrations in the brick shell. Gaps appear where metal meets masonry. The charging mechanism at the top of the stack, designed to sit flush with the throat opening, now protrudes awkwardly, its supporting framework stressed by the downward movement of the structure beneath it. The sounds change too. During the third week of December, workers begin reporting creaks and pings from the iron bands, not the normal thermal ticking of hot metal cooling and heating with the daily cycle, but sustained groans that last for hours, the sound of metal under increasing tension. The lowest band, a massive ring of wrought iron 8 inches wide and 3/4 of an inch thick, develops a visible bow between its support lugs, the metal flexing inward, as though being drawn tight by an invisible hand. One night shift worker, a man named Peterson who has worked blast furnaces for 15 years, describes the sound as similar to the noise made by overtensioned boiler straps just before they're released. A high, stressed ring that carries through the foundry floor and makes men uneasy. It's the sound of metal being asked to do something it doesn't want to do, he tells the shift supervisor. It's the sound you hear before something lets go. Engineering staff install permanent monitoring stations. Fixed points marked on the foundation, corresponding points marked on the iron bands, measured 3 times daily with calibrated instruments. The data shows contraction continuing at a steady pace, now approaching 1 1/4 inches total. The rate hasn't increased dramatically, but it hasn't stopped either. Whatever mechanism is driving the change remains active, relentless, indifferent to observation. The clearances around the tires, the copper nozzles that inject air into the combustion zone, begin to close up. The nozzles, mounted in the brick shell and designed with deliberate spacing to allow for thermal movement, now sit compressed in their openings. 2 of them require cutting and refitting to prevent the brick from crushing the copper entirely. The work is done hot, with the furnace in full operation, men working in rotating shifts of 15 minutes to avoid heat exhaustion. Holbrook orders the installation of strain gauges on the iron bands, simple mechanical devices that measure how much force the metal is experiencing. The readings confirm what the sounds already suggested. The bands are under increasing compression load, being pulled inward by the contracting brickwork, resisting with the immense tensile strength of wrought iron, but showing measurable deflection. It's a tug-of-war between brick and iron, and the outcome remains unclear. The first theory to gain serious consideration is foundation failure, not obvious settling, but some form of subsurface void or compression zone that's pulling the entire structure downward while keeping it superficially level. They bring in a mining engineer who specializes in underground stability. He sinks test borings around the foundation, extracts core samples, examines the bearing strata. The ground is solid. Dense clay over bedrock, no voids, no water infiltration, no evidence of subsidence. Whatever's happening, he concludes, it's not the earth moving. The second theory is structural collapse, a progressive failure of the internal refractory lining, crushed under its own weight, and the pressure of the iron column inside, settling downward and dragging the outer shell with it. But the furnace continues to operate normally. The iron quality remains consistent. The internal temperature profile, inferred from the color and behavior of the flame at the top and the composition of the slag, shows no signs of lining failure. If the refractory were collapsing, the furnace would be hemorrhaging heat, producing inconsistent iron, showing visible distress. It does none of these things. Sabotage enters the conversation briefly, whispered among workers, but never formally proposed. The idea that someone might be deliberately undermining the structure, weakening the foundation, or tampering with the brickwork gains no traction once the measurements are examined closely. The contraction is too uniform, too consistent, too mechanical to be the work of human interference. It has the character of a natural process, something governed by physical law rather than malicious intent. One of the consulting engineers, brought in from Pittsburgh, suggests differential cooling, the idea that some portion of the furnace is cooling while another portion remains hot, creating uneven contraction that manifests as overall shrinkage. But the furnace has been in continuous operation for 10 months without shutdown. There is no cooling zone. The entire structure exists in a state of sustained thermal exposure, every brick and every iron band heated to equilibrium with the process inside. They are running out of conventional explanations. The furnace continues to contract, now approaching 1.5 inches total, and no theory adequately explains why a structure exposed to extreme heat that should be causing expansion, is instead growing smaller. The phenomenon defies the basic expectation that materials expand when heated and contract when cooled. Something else is happening, something that requires looking beyond simple thermal behavior. The breakthrough begins with an observation by Thomas Kirby, the head mason, during a routine inspection in early January. He's examining the brick surface through a magnifying lens, looking for cracks or spalling, when he notices something unexpected. The individual bricks in the lower courses appear denser, more compact than the bricks higher up the stack. The surface texture is different, tighter, as though the material has been compressed. He brings this to the attention of Samuel Brennan, the materials engineer who sourced the original refractory brick. Brennan examines samples from different heights using a micrometer and a simple crushing test. The bricks from the lower courses are measurably smaller in dimension than when they were installed, and they're harder, more resistant to mechanical pressure. The bricks from higher up show less change. The pattern correlates exactly with temperature. The hottest zones show the most dimensional change. Brennan orders a chemical analysis. The refractory bricks, like most fire bricks of the era, contain a small percentage of chemically bound water, not free moisture that evaporates quickly, but water molecules integrated into the crystalline structure of the clay. Under sustained heat, particularly heat maintained for months without interruption, this bound water is slowly driven off. As it leaves, the crystal structure collapses slightly, the material densifies, and the brick shrinks. It's a small effect, perhaps 1 or 2% of total volume, but spread across thousands of bricks and sustained over months, it adds up. The brickwork is contracting from the inside out, each individual unit growing slightly smaller as it loses structural water under the relentless heat of the furnace. But this explains only part of the phenomenon. Pure shrinkage of the refractory alone wouldn't account for the visible compression of the iron bands or the stressed sounds coming from the metal framework. Something else is contributing, some interaction between the shrinking brick and the restraining forces of the iron hoops. The engineering team begins examining the system as a whole rather than as individual components. The brickwork wants to shrink. The iron bands resist that shrinkage, holding the structure in place with immense tensile force. But the brickwork is also trying to expand thermally. Hot materials push outward. The iron bands constrain that expansion too, creating a compressive stress within the brick. The result is a complex balance. Thermal expansion pushing out, volumetric shrinkage pulling in, iron bands resisting both, all happening simultaneously under sustained heat. And there's more. The furnace isn't a uniform cylinder. It's a tapered stack with varying wall thickness, different temperatures at different heights, and different stress patterns in different zones. The lower sections experience more load from the weight of material above. The upper sections experience higher thermal exposure from rising gases. Each zone behaves differently, shrinks differently, responds to constraint differently. The measurements now take on new significance. The contraction isn't simply the brick getting smaller. It's the brick getting smaller while being squeezed by iron, while trying to expand from heat, while supporting massive vertical load, all of which creates internal stress that manifests as net dimensional change in complex and counterintuitive ways. In late January, Holbrook authorizes a comprehensive stress analysis, the most detailed examination yet attempted. They construct a scale model of the furnace using mathematical calculations and mechanical analogues, springs and weights that simulate the forces acting on the structure. The model isn't perfect, but it allows them to explore scenarios. What happens if the brick shrinks by 1%? By 2%? What if the iron bands resist? What if they yield slightly? The model produces results that match the observed behavior. When the brick shrinks under constraint, the structure doesn't simply get smaller uniformly. Instead, Stress concentrates in particular zones, especially where the iron bands attach and where changes in wall thickness occur. These stress zones experience additional compression, which can cause creep, the slow, permanent deformation of materials under sustained load. Creep is a known phenomenon in metals at high temperature, but it also occurs in ceramic materials like refractory brick. Under enough pressure, maintained for enough time, the brick doesn't just shrink from moisture loss, it deforms, compressing further under its own weight and the constraint of the iron framework. This compression is permanent. Even if the furnace were shut down and allowed to cool, the brick wouldn't spring back. The dimensional change is locked in. They measure the iron bands more carefully now, looking for evidence of yielding. Wrought iron is strong in tension, but it's not infinitely rigid. Under sustained load, it will stretch microscopically. The measurements confirm this. The bands have elongated slightly, stretched by the inward force of the contracting brickwork. The stretching is small, perhaps a few thousandths of an inch, but it's real, and it represents stored elastic energy in the metal, force that's constantly trying to compress the brick even further. The thermal stratification adds another layer of complexity. The furnace isn't uniformly hot. The combustion zone at mid-height runs hotter than the top of the stack or the bottom hearth. This creates different expansion rates at different heights, which in turn creates shear stress where hot zones meet cooler zones. The brick can't slide freely. It's locked together by mortar and by its own weight. So the differential expansion creates internal stress that manifests as compression in some areas and tension in others. And then there's gas pressure. The interior of the furnace operates at slightly above atmospheric pressure, maintained by the blast of air from the tires. This internal pressure pushes outward on the refractory lining. In a normal state, this pressure would help expand the furnace, pushing the walls outward. But when the brick is already under compression from thermal constraint and moisture loss, the internal pressure changes the load path. Instead of pushing the walls out, it compresses the brick vertically, adding to the overall contraction. The picture that emerges is one of multiple effects working in concert: moisture-driven shrinkage, constrained thermal expansion, creep under load, iron band compression, thermal stratification, and internal pressure. No single effect dominates. Instead, they combine, each amplifying the others, creating a net result that appears simple. The furnace is getting shorter, but arises from a complex interplay of material behavior under extreme conditions. The final report, delivered to Holbrook on February 9, 1892, runs to 43 pages of calculations, diagrams, and material analysis. The essential conclusion is stark. The blast furnace at Riverside Iron Works has contracted because it was designed to expand, and the constraints placed on that expansion, necessary constraints dictated by structural stability, have converted thermal growth into compression and permanent deformation. The primary mechanism is moisture loss from the refractory brick. Under sustained heat, chemically bound water is driven from the clay structure, causing the material to densify and shrink by approximately 1.5% of its original volume. In a structure containing over 3,000 cubic feet of refractory material, this translates to significant dimensional change, easily enough to account for the measured contraction. But the brick isn't free to shrink uniformly. It's constrained by iron bands designed to prevent the furnace from expanding outward and bursting under internal pressure. These bands, wrapped tightly around the structure, resist the shrinkage, creating compressive stress within the brickwork. This compression doesn't stop the shrinkage, it redirects it, causing the brick to deform in ways that minimize volume while accommodating the constraint. The result is vertical compression, the structure pulling itself downward as the brick seeks to shrink in the direction of least resistance. The thermal expansion of the brick, which under normal circumstances would cause the furnace to grow taller, is also constrained by the iron bands and by the massive weight of the structure itself. The brick wants to expand, but it's held in place by forces that prevent free movement. This creates internal compressive stress that adds to the stress from shrinkage. The brick is simultaneously trying to expand from heat and contract from moisture loss. and both tendencies are resisted by constraint, resulting in a complex stress state that favors permanent compression. Creep compounds the problem. Under sustained compressive load at elevated temperature, the refractory brick undergoes slow, permanent deformation. The material doesn't fail catastrophically, it simply yields, compressing incrementally over weeks and months. This creep is accelerated by the high temperatures and by the cyclical loading from daily variations in furnace operation. Each heat cycle introduces additional stress, and each stress cycle contributes to permanent deformation. The iron bands themselves contribute to the contraction. As the brick shrinks and pulls inward, the bands are stretched elastically, storing energy like a spring. This stored energy exerts a continuous inward force on the brickwork, compressing it further. The bands are strong enough to resist breaking, but they're not rigid enough to prevent deformation. They bend slightly, bow inward between support points, and in doing so, they add to the compressive force acting on the brick. Thermal stratification creates differential expansion at different heights. The hottest zones experience the most thermal expansion and the most moisture loss, while cooler zones experience less of both. This creates shear stress where zones meet, and this shear adds to the overall stress state. The furnace doesn't contract uniformly top to bottom. It contracts more at the bottom, where temperatures are high and loads are greatest, and less at the top, where conditions are somewhat milder. Internal gas pressure, maintained at roughly 2 pounds per square inch above atmospheric, pushes outward on the refractory lining. In a structure that's trying to expand freely, this pressure would help push the walls out. But in a structure already under compression, the pressure changes the load path. It compresses the brick vertically, adding to the downward force and contributing to the overall contraction. The effect is small compared to other factors, but it's measurable and it's continuous as long as the furnace operates. The conclusion is that the Riverside furnace has contracted not despite being under extreme heat, but because of a specific combination of heat, constraint, material properties, and sustained loading that created conditions favoring permanent compression. The phenomenon is rare because it requires sustained operation at high temperature for extended periods, conditions that most furnaces of the era didn't experience due to regular shutdowns and maintenance cycles. The Riverside furnace, kept in continuous operation to meet production demands, provided the perfect environment for the effect to manifest. The recommendations are practical. Continue operation, monitor the contraction, adjust clearances and attachments as needed, and plan for eventual shutdown and rebuild when the deformation interferes with function. The furnace isn't in danger of catastrophic failure. The compression has actually made the brick stronger in some respects, denser and more resistant to thermal shock. But it has changed the geometry, and eventually those changes will accumulate to the point where operation becomes impractical. By the time the furnace is finally shut down in October of 1893, it has contracted a total of 2 1/8 inches. The rebuild reveals brickwork compressed so tightly that some courses have to be cut apart with chisels. The iron bands, when removed, spring outward with audible pings, releasing stored tension. The entire structure, disassembled piece by piece, tells the story of materials pushed to their limits, responding to forces in ways that weren't fully understood until they were carefully measured and analyzed. The phenomenon becomes a case study in engineering schools, a reminder that material behavior under sustained extreme conditions can be counterintuitive, that expansion and contraction aren't simple opposites, and that constraint matters as much as temperature. The furnace that shrank while burning remains, decades later, a lesson in the complexity hidden within what appears simple: heat, brick, iron, and time.